Good morning. We will continue our discussion with respect to the vibration of atoms in a lattice, which is the phonon energy, vibrational energy. So, yesterday we had derived the relationship between the vibrational frequency, this omega, and the wave number kappa, right. So, this is the dispersion relation that we had derived for with respect to the phonons. And we see that this is related to the spring constant, the mass of the atom. We have only one monoatomic lattice here, and this kappa here is the crystal wave vector, which is 2n pi by the length of the crystal. So, this is discretized now because of the discrete values of kappa that it can take, and we relate now this to the actual quantum mechanical phonon vibrational energy, the vibrational energy derived for a simple harmonic motion from quantum mechanics. The only difference being there we had a simple relationship for the frequency. Now, we are going to substitute this with the dispersion relation that we had obtained. So, the dispersion relation itself has been obtained from just simple classical mechanics and substituting a wave solution into that, and finally discretizing the wave solution, correct. So, this is basically how we are approaching this vibrational energy level calculation for the phonons. If you plot it, I think probably if you tried yesterday to see how this dispersion relation looks, that means we have omega on the vertical axis, and once again you can plot either a non-dimensional kappa or just kappa as it is. If you plot kappa a by pi also, that should be fine. So, how these are basically sine functions, but and these are absolute values. So, only you will see everything in the positive values of omega, right. So, therefore, if you vary your kappa, let us say this is your 0, you have minus pi by a, minus pi by a to plus pi by a. So, these are values of kappa. I am just varying by changing the values of m, for example. So, and then you have 2 pi by a, 3 pi by a, and so on. Similarly, here you have minus 2 pi by a, minus 3 pi by a, and so on. So, typically you will have the maximum at what point? Suppose you substitute pi by a for kappa. So, this becomes sine pi by 2, which is equal to 1. So, that is the maximum value of omega that you will be getting. So, you get a maximum here, and from there you will be again dipping down at 2 pi by a. What happens if you substitute? 0. So, similarly you have a symmetry about this, therefore, for the negative values of the wave number also you will be. So, this now it is going to be periodic and it is going to repeat. Okay. So, this will reach maximum here and so on. So, this is how the dispersion looks in this case. Now, as you can see, the values of kappa are also now discrete, right. So, these are not actually continuous bands again, but these are quasi continuous. For discrete values of m, these kappa values are now discrete and you have corresponding values of omega. So, you can actually, to be more accurate, you have to denote this by means of these quasi continuous bands. Now, we will see why we have drawn in this particular units of minus pi by a plus pi by a, and what is the significance of this block here. So, the block between minus pi by a to plus pi by a, and as you can see from between this minus pi by a to plus pi by a, it looks like a unit cell. Okay, you have the dispersion and about which it is periodic and repeating. So, again if you say minus then you go from pi by a to 3 pi by a, 2 pi by a or 3 pi by a. So, now this becomes repeating in structure. So, about the center line between minus pi by a and pi by a, that is totally for the width of 2 pi by a. So, it is one unit cell and then it keeps repeating every 2 pi by a, correct. So, we will see what is this to do with 2 pi by a. Okay. So, to understand, so this will be actually the unit cell of the crystal itself. So, this I will just give you the name right now. So, this is called the Brillouin zone. So, let me write down the exact spelling, Brillouin zone. Okay. So, this Brillouin zone is nothing but the unit cell of the crystal, and about which you can say your dispersion or your energy relationship with wave vector keeps self repeating. Okay. So, your analysis more or less can be confined only to one periodic Brillouin zone. So, you do not have to do this for the entire crystal, just one Brillouin zone, and the solution will also be periodic and repeating. Okay. So, in crystals in solid state physics, in crystalline materials, usually these analyses are confined to only one Brillouin zone width. So, which spans from the wave vector of minus pi by a to plus pi by a. So, we will also show that. So, another thing I want to talk about is the vibration of these phonon waves. If you look at these atoms now, so you are talking about atoms which are periodically spaced. So, this was our one dimensional monoatomic chain of atoms in a crystal. Okay. So, these were separated by the lattice constant A, right. So, in our if you look at the wavelength of these phonon vibrations. Okay. So, what will be the minimum wavelength that you can minimum wavelength, let us say lambda min for these phonon vibrational waves that is possible. So, you can imagine the minimum wavelength to take this form here like this. You understand? This is the minimum wavelength that is possible when you talk about these phonon vibrational waves which are propagating maybe as a right running wave, correct. So, if you therefore look at lambda min, what is the minimum wavelength possible? 2a, right. So, you cannot have wavelengths which are smaller than 2a because there are no atoms. Okay. So, physically it does not make sense if you are having phonon vibrational wavelength smaller than the separation between the atoms, correct. So, this is the minimum wavelength. So, therefore, your wavelengths are now constrained due to the positioning of these atoms. Okay. Your lambda has to be what? Greater than or equal to 2a. So, this is an important condition that these phonon vibrational waves have to satisfy, right. So, if we therefore based on this, if you divide by pi on both sides, so you will have lambda by 2 pi. greater than or equal to a by pi, or if you take reciprocal of this, you have 2 pi by lambda pi by a, and what should the sign be? Less than or equal to. So, which means what is 2 pi by lambda? Wave number k should be less than or equal to pi by a. Okay. So, or in other words, so what we are saying is, this is basically the boundary, okay, of the Brillouin zone. So, therefore, your plus or minus pi by a that we have chosen, okay, is because of the fact that pi by a marks the boundary of the Brillouin zone, beyond which it does not make any sense to look at the solution. Okay. So, we are confining our entire solution to this Brillouin zone because of the fact that your k is less than or equal to pi by a. Okay. So, this is one thing, and now we can continue this analysis a little further, and we can also substitute. Now, this k here is nothing but kappa. Okay. So, I am just going to use kappa here, so that you do not confuse with the other k, it is your spring constant. So, we are also having a constraint in the crystal that k is equal to 2 pi m by L, okay, where m is equal to plus or minus 1, plus or minus 2, and so on. Therefore, from this can you derive a relationship between your m and this L is nothing but capital N times A, where N is the number of atoms and A is the lattice spacing. Can you derive a relationship between M and N? So, now you have this constraint here for the crystal, and you also have this constraint for the phonon vibrational waves. Okay. So, equating these two, derive a relationship between M and capital N. M is less than or equal to n by 2. So, what do you understand from this? M is less than or equal to n by 2. So, if there are n number of atoms, and what is M here? You can interpret this as allowable quantum state, right, because these are discrete. So, these are representing the quantum states or the separation in K, okay, discretized due to the crystal structure itself. So, these allowable quantum states should always be less than or equal to n by 2. So, now therefore, the maximum number of quantum states that are possible from 0 to pi by a, how many are possible? N by 2. Okay. So, therefore, if you go about the unit cell I have drawn here from minus pi by a to plus pi by a. So, therefore, how many number of maximum possible quantum states are allowed? N, capital N. So, between 0 to pi by a you have n by 2 number of quantum states. So, therefore, from minus pi by a to plus pi by a, the maximum allowable number of allowable quantum states are basically nothing but capital N. That means what? So, if you are drawing this, okay, the number of these discrete points are basically, if you count them, they will be capital N between minus pi by a to plus pi by a, right. So, this is how they are discretized. So, because these kappa is now discretized for different values of m, and then we have seen for this case the maximum allowable values of m between minus pi by a to plus pi by a is capital N. Therefore, when you are drawing this discrete representation, you can break this into n discrete points between minus pi by 8. So, within this Brillouin zone you have therefore capital N number of quantum states, maximum number of quantum states possible. Okay. So, this is a very important concept. So, one thing is you have for the phonon vibrational waves, you have a constraint on the minimum wavelength of these phonon waves, it cannot be smaller than the lattice spacing for sure, and at the same time we also have a constraint on the wave number for the crystal. So, from this we know what is the maximum number of quantum states allowable within this Brillouin zone, right. So, now what we will do is, if you therefore draw the representation of this just like we did for the electrons, in the electrons also, since it was symmetric, we draw about the vertical axis only one half of this energy bands. The same way usually for the phonons also you draw the k a by pi, on the vertical axis you have the omega, and you just only draw this part. So, this is spanning from 0 to k a by pi. What should be the maximum value? For k pi by a, this becomes 1. Okay. So, this is the dispersion curve that is generally plotted for phonons, okay, because they know that this is symmetric and therefore they avoid the other side, but do not think that this is the only one, it is actually symmetric about the vertical axis, just like the way we plot it for the electrons. The electrons can be plotted like this, okay, but this is also symmetric, right. So, this is the dispersion curve that we get. Now, in the case of one dimension, we get only one dispersion curve, and this is corresponding to what kind of vibration it is, only in the x direction. Okay. So, these are called longitudinal phonons. So, these are longitudinal vibrations, right. And the slope of this dispersion curve, that is basically d omega by dk, will give you what? It will give the wave velocity. So, that is nothing but the speed of sound in the lattice, because the longitudinal waves are corresponding to basically the acoustic waves. Okay. So, that is how the sound will propagate within that particular crystal. So, if you want to calculate the acoustic velocity, okay, you have to take basically the slope of this dispersion curve, and that will give you the speed of the propagation of the acoustic waves, which is also the speed of the longitudinal phonons, right. You understand now. So, this is only one kind of mode that we are getting in the one dimensional picture. Okay. So, if you are now translating this into 3 dimensions, so right now we talked about only longitudinal vibrational modes. Okay. So, if you are extending this to a 3-dimensional system where you have the longitudinal vibration along the x, okay, and you have a similar structure along y and similar structure along z, So, this is going to be your longitudinal mode, and what are these? These are going to be transverse modes. So, in the perpendicular directions to the longitudinal mode you have the transverse modes. So, therefore, for this 3 dimensional system, if you plot the dispersion curve omega versus k, so now you will be able to see this longitudinal mode, and also you will have transverse modes. These are your transverse modes of vibration, you understand. So, you are talking about now a vibration in the longitudinal direction and also vibrational waves which can travel like these. So, these are your right running waves. These waves can also propagate in this direction and also in vertical direction. So, these transverse waves will also contribute to the dispersion, and they will have a separate set of dispersion curves. Okay. Is the point clear? So, they will also have, suppose you take the slope of the transverse modes, so they will also correspond to certain velocities. Okay. So, that those are not the speed of sound, but they are the speed of the transverse phonons. Okay. So, they are also important when you talk about the contribution of heat transport. The heat transport, all the 3 modes will contribute to heat transfer, the phonons which are propagating in the longitudinal direction as well as in the transverse direction. So, we have to have the information of the velocity of phonons for all the 3 modes from the dispersion curve. So, the dispersion curve is important in the sense that not only do you understand how the frequency, angular frequency varies with wave vector, but also to do any analysis of heat transfer, the velocities, the respective phonon velocities are obtained from this curve. Okay. So, now let us consider a slightly more complex structure of atoms. So, we have assumed a monoatomic atoms in a crystal. Now, let us do a polyatomic lattice chain. So, wherein you have one large mass, large atom, one smaller atom, they can be of different masses. So, we will call the mass of the large atom with the capital M, mass of the small atom with the small m. So, this is a polyatomic structure, and you can have many of this now repeating to form a crystal. Okay. So, the next one will be again a large one, and again you have a smaller one, and now this keeps self repeating. So, the interaction between the larger atom and the smaller atom, okay, this is a polyatomic structure. So, this could be some K1, and the interaction between so this is K1, and then you can have the neighboring ones between this and this to be K2. Okay, you can have 2 different lattice constants in principle, and this can be self repeating. Again you have K1, K2 and so on. So, you can have therefore the entire lattice formed with these larger and smaller atoms, and again the separation between the 2 atoms can be A1, and the separation between these 2 here is A2. Okay. So, we will also, so this total, this is the entire lattice spacing A. So, this A is broken down into the spacing between the larger one and the smaller one A1, and between the smaller one and the next larger one A2. And also we can number these nodes. For example, the larger ones we will call these with the notation JA, then this is J plus 1A. So, we are using the conventional notation we used earlier for the larger ones, and this is going to be J minus 1A. And for the smaller ones we will use slightly different convention. For example, we will call this with the half integer location, because it is between j and j plus 1, we will call this as j plus half A. Is it okay? So, what we are assuming now is that A1 is equal to A2 is equal to A. So, let us A by 2, sorry. So, let us just say that they are equidistant, and also the fact that K1 is equal to K2 is equal to K. We are also assuming that the spring constants are equal. So, this is your half integer atom, the smaller one, and what about this J minus half A. Okay. So, with this kind of a notation, now you can go back to the earlier case where we wrote down the force balance, right, and rewrite it now for one for the larger mass m and the other for the smaller mass small m. So, we will also call the relative displacement from equilibrium for the larger atoms to be u. This is for the larger mass, and we will use the notation V as the relative displacement for the smaller mass or the half integer atoms. So, we will have therefore two sets of equations, one for the larger mass and one for the smaller mass. That means, whatever we have written down here. So, what we call this as equation 1A, or even one step before that. Okay, so, a 1A, you can rewrite this 1A for both the larger and the smaller atoms. You know the neighbors now, we have used the corresponding convention. So, the larger mass, what will be the equation of motion? M into d square. You let us write it for the atom J. Okay. uj by dt square will be equal to k times. Now, this will be influenced by the smaller atom on the right and the left, right. So, therefore, we have the relative displacement of the smaller one, which is V j plus half A, and then what do we have? Okay, plus j minus half A, and then minus 2 times uj, right. So, the relative displacement from equilibrium of the present atom, the neighboring atoms are the smaller ones. Okay. So, similarly, for the smaller mass, we have d square V, let us write this for j plus half by dt square. So, this will be k of, what do we have for this j plus half, this atom? We have j plus 1 and we have j. Okay. So, you can write this in terms of u j plus 1 plus you have u j a, and we have minus 2 v j plus half a. Okay. So, with this you can once again assume the wave solution to this problem. So, we will substitute the assumed solution for uj to be once again a e power minus I omega t minus k j a. This is the discrete wave solution for uj, what we assume, and this can be substituted into this equation here, and the other solution what we will assume for v j plus half will be some b e power minus I omega t minus k into j plus half a, right. So, both are right running waves. So, the net displacement is resulting in right running waves for both the larger atom displacement and the smaller atom displacement. Okay, so, you have therefore two sets of waves, one due to the motion displacement of the larger atoms, one due to the displacement of the smaller atoms. And I will just give you the solution. You can actually continue this, you can put it into that equation and get the dispersion relation for this case also, only that it looks a little bit bigger. I will just give you the final solution for omega. So, you will have omega square will be spring constant, we will call this kappa here, okay, this kappa, to distinguish this from k. So, we have 1 by m1 plus 1 by m2, sorry, this should be capital M, here small m. Okay. So, this is the larger mass, small mass, this is the harmonic mean between the two, plus or minus you have again spring constant into 1 by capital M plus 1 by small m the whole square minus 4 times sine square kappa a by 2 by capital M times small m the whole raised to the power 1 by 2. So, this is the dispersion solution for this case where we have a polyatomic, that is we have two atoms now, one larger mass, one smaller mass, and this is how. Now, therefore, if you look at the dispersion, you have a plus or minus here. So, that means not just one branch, but we have two branches of waves. So, effectively what is happening is you have a wave from the larger atom displacement, wave from the smaller atom displacement. They can either be out of phase or they can be in phase with each other. Okay. So, the out of phase waves will correspond to a motion like this. So, you have one wave from the larger atom displacement like this, the out of phase will be this is from the smaller atom displacement. Okay, you can call this as u and this as v. These are the waves coming from the two respective displacements, and they can be out of phase like this, or they can finally be in phase like this. So, this is your out of phase component. So, which one of these require more energy to vibrate? The out of phase component or the in phase component? Why in phase component? But the out of phase one actually consumes more energy. Huh? One is trying to basically move in one phase, the other in the opposite phase. So, this actually consumes more energy than the in phase component, if you look at it. So, therefore, if you draw the dispersion curves now, what happens? Let us still stick to 1D now. So, you have your in phase component, which is giving to an effective right running wave, which is your longitudinal phonon vibration, and on top of that you have an out of phase wave, which is also running effectively in the right, but this one is going to consume more energy than the in phase one, because they are trying to be out of phase with each other. So, therefore, if you plot this value will come out to be something like this. So, this is your out of phase. So, therefore, the positive sign here should correspond to the out of phase wave and the negative to the in phase. So, this out of phase wave is also called optical mode or optical branch of phonons, and the in phase is called the acoustic branch, because as we said that this slope of this will give you the speed of sound in the lattice. So, this is your longitudinal vibration corresponding to the speed of sound propagation, whereas the other one, the out of phase one, corresponds to this is a higher energy mode of the phonon vibration, which is usually associated with interaction with electromagnetic waves, for example. So, one phenomena that we can observe with these optical, why it is called optical, is they can interact with the photons. So, when you have a photon and phonon interaction, the optical branch of phonons are the ones which will get the energy from the photons. They are the ones which can directly interact with these electromagnetic waves, and from there transfer or decay into finally the in phase or acoustic branches. So, you see, so this is how the photon phonon coupling can happen. You understand? So, for example, if you have a semiconductor solar cell and you expose it to UV radiation, So, you have absorption of the photons, some heat generation is also happening within the semiconductor material. So, how this is happening is because of the photon interaction, and that is coming from the optical branch, which is basically first interacting with the photon light waves and transferring that energy to the acoustic branch, which is now dissipating this as heat. So, this is a very complex process, it has not been very clearly understood, but from the dispersion relation you know that there are two branches possible, but it is not very clear the mechanism of how the optical branch can interact with photon and then how it can degenerate into an acoustic branch. All right. So, this is from a relatively simple analysis, from the analytical solution we could reach this point. Now, what happens in a 3-dimensional crystal structure? Now, how many modes of out of phase waves can exist, how many modes of in phase waves can exist? So, you can now extend this to another 2 corresponding to the transverse in plane or transverse in plane or acoustic branches, and similarly you will have 2 more sets. So, the highest one will be corresponding to the longitudinal optical phonons and the other 2 branches will be the transverse optical phonons. So, for a real 3D crystal, so you can therefore end up with so many branches. So, one is your acoustic branch and you will have first the longitudinal ones and you will have the transverse. So, this is your longitudinal acoustic phonons. So, people use this convention, LA means longitudinal acoustic, then you can have transverse acoustic, you can have TA1, then you can have TA2, and in many crystals like silicon for example, it is a common semiconductor material, the 2 transverse acoustic branches exactly overlap on top of each other. Okay. So, similarly if you look at the optical phonons, so you can have different branches, you can have longitudinal optical phonons, you have transverse optical phonon 1, transverse optical phonon 2. So, in general if you have m atoms in a basis, okay, in a monoatomic chain you have only 1 atom, in a diatomic you have 2, triatomic 3. So, if you have m atoms in basis, so how many acoustic modes are possible? So, you have m minus 1. If suppose m is equal to 1, so in this case it should be no sorry. So, in this case it should be just a moment. So, 3 you should have 3 acoustic modes, and in case of optical modes you have 3 into m minus 1, right. This is your general thumb rule. So, therefore, if you put m equal to 1 into this, for a monoatomic lattice chain you have 3 acoustic waves in 3 dimensions, and 0 optical modes. And then if you have a diatomic, it should be simply 3, because the M atoms are only influencing the optical modes. By default you will have 3 acoustic modes, okay, but if you are having M number of atoms, say 2 atoms diatomic chain, then you will have 3 optical modes. This is what we see here. If you have 3 atoms in the basis, so you have 6 optical modes. So this is your general thumb rule calculation. If you want to understand how many modes of acoustic phonons, optical phonons are there, so you have to apply this thumb rule. Is it clear? So in a 3D crystal. So we will kind of I think we have given broad overview about the dispersion of phonons in a crystal, and also the fact that you have the branching of these phonon dispersion. So due to the vibration in one direction and in the other directions, and also due to in phase and out of phase phonon waves. Okay. So what we will do is, you just right now you just have to understand this, but when we solve the heat transport problem, you will understand how these dispersion curves are used for the transport of heat. So in the next class tomorrow we will complete the solid state physics. So we will focus on the last part, which is called the density of states. So this density of states is now the bridge when we go from the quantum mechanics to statistical thermodynamics, because now we have seen that whether it is a simple system or whether it is a real crystal structure, you have quantization of the wave vector space, quantization of the energy or the omega whatever. So now we have, if you plot therefore the 3-dimensional wave vector map, that is kx, ky, kz, you are going to plot all discrete points corresponding to these values of m, l and n, right. So therefore how useful is this, so many random discrete points for us? We cannot keep track of the variation of the quantum state, each and every quantum state. There are so many quantum states, and in 3 dimensions, all 3 dimensions are discrete quantum states. So how useful is bookkeeping all these discrete quantum states? So we cannot have all these information with us. So what we will finally do is take a band, continuous band, and then average out these discrete states. Okay. So this is called density of states. So we need to do this before we slowly transition to the macro scale to calculate the properties. So somehow we have to average out the individual quantum states by taking bands, and within these bands we will count how many of these quantum states are existing, and then directly use the density of states for calculating the macro scale properties. And now we will slowly do away with all these micro states. Okay. So the next topic tomorrow we will introduce the density of states for electrons and the phonons both. Okay.